Let's make a simple experiment first. I mean, today we will be studying, starting to discuss the electricity. Now let's imagine that you don't know anything about electricity. Electricity is not yet discovered, but you know about the Newton's dynamics. You have studied 109 course, you know all the dynamics, the forces and the torque, etc. Now we will make an observation. Here, can everybody see this? Well, it's basically a simple setup where there is a very thin string, and at the end of the string, I attach the pencil, a pen. So this is my setup. And it's in equilibrium. So what does it mean that something is in equilibrium? So what can you say about the forces acting on this thing? F total is 0. And the torque is also 0. So those two things are the requirements for equilibrium. Now let's see what happens if when I bring this thing close to it. Nothing. So the net force is still 0. So this is an experiment which just reproduced some null result. We don't have the result that we have. That's a valid experiment, so there's nothing new. I mean, in fact, if you think of most of the experiments that we do, they just don't give up any unexpected results. So we just either see what we expect or we don't see anything new. So let's give it another try. So what do you see? So what do you observe? So what do you observe? Did you observe anything? I did not. I mean, it's vibrating a bit, but that's practically what we observe. Okay, do you have something under your sweatshirt? May I take it? When I was wearing that one and took it off, it worked. But I just didn't want to undress myself. So let's give this one a try. Still nothing. So what do you suggest? What shall we do? Okay, so let's see. Can that be the reason? You see, whenever we do experiments, we can put some upper bounds. We cannot put any exact value. We have some experimental limits. So what your friend is saying that it's very heavy. What will be our sensitivity? What do you guess? If it is too heavy, that means we can only measure forces that are very large. So if we are not measuring anything, that means if there is a force, it should be smaller than that upper bound. So in this case, what do you think is the upper bound? What would you guess? Just make a guess. Can we measure like 10 newtons? Let's say the object is 100 grams. So its weight is 1 newton. So if we exert a force in the vertical direction, let's say, that is larger than 1 newton, we will be able to lift it up. So definitely, if there is a force, it is less than 1 newton. That is the force. I mean, that we can say by studying this one. Now, what about the torque? Because if we are exerting a force on it, we have to overcome its weight. We want to lift it, which is at the order of 1 newton. If we cannot exert such a force, we will not be able to lift it. What about the torque? Is there a torque acting on this one? I mean, you see, we know that the total force is 0 because there are basically two forces acting on it, the tension force and the weight. So if we exert a vertical force upward, we will be changing the tension until we exert 1 Newton in the vertical direction, and once we exert 1 Newton in the vertical direction, the tension will be 0 and it will start moving up. What about the torque? Is it the torque is 0 because different torques cancel each other? There's no torque. I mean, the two forces do not create any torque. So regarding the torque, we will be quite sensitive. So if there, I mean, the sensitivity will be probably much better than 1 Newton. Well, you see, the difference between the other one and this one is, I mean, I'm not trying to lift it up anyway. I'm trying to make it rotate. The forces are vertical. So I'm trying to exert a horizontal force. So, I mean, also in the vertical case, the tension is changing, which is not something we are measuring. And if we could measure the tension, we could even have a larger sensitivity than 1 Newton, but we are not measuring the tension. So we should be measuring the tension to say if there is a force or not. Well, let's see. Now there was a Now there is a small deflection, a small one. I will create a better one after the break. Okay, probably also when you are wearing a pullover or something made of synthetic material in the dark, when you are putting it up, pull it off, you know, or pull it on, you probably hear the small sparks. Hear them, you can even see them. Now let's come back to this example. Those sparks are what we are looking for. So what can you say? There was a small deflection. This is, by the way, what we call a torsion balance. So it's by measuring the torque created on this object, you can measure very small forces. It's highly sensitive, and even this one will be quite sensitive. Because there is no restoring torque acting on this one, at least in its equilibrium state. And the torque created by this spring, I mean, you see, if you shift it slightly, it will just oscillate back and forth. So that's an oscillation. We can measure the frequency of that oscillation. Once we determine the frequency of that oscillation, we can measure the so-called torque constant, just like the spring constant. So once we know the spring constant, we can determine how much torque it exerts for every rotation. Let's say if this object rotates like 50 degrees, then you will, by knowing this torsion constant, we can determine how much torque that the string is exerting, so how much force is being exerted on this object. So you can even measure gravity using this. The Cavendish experiment is basically such an experiment that we use to measure Newton's constant. Okay, so we observe this very small deflection. So what can you say? There's some, well, not a net force. You see, the center of mass didn't move. It just rotated. So there's some torque created, and hence there is a force. So what can, I mean, this force was nothing like that we had observed before. And it could have been gravitational force, because another property of this force is I didn't touch that object. But nevertheless, there was a force acting on it from a distance, just like gravity. There is this new force which acts from a distance. And, well, that's basically all we can say for the time being. And when the people were making these experiments, they charge the object using what's called the amber. Do you know amber? Kehribar. Now you also make necklaces or bracelets. You know what it is? Okay. You know the Greek name for that? So does anybody know the Greek name for Kehribar or? Yes? You all know the name. It's electron. It's called electron. So that object. So that's where the name of the electron also, the electricity or the electric, etc. comes from. So people used to do experiments with that thing, and so they called the phenomena relating to electron. Now, of course, now we know much more than that. I mean, we have been doing many experiments on electricity. We know all the properties after the observation of this phenomena. The first thing you would like to do is, how does it change? What does it depend on? So one thing we know is, okay, it depends on the distance. Again, by using such experiments, we can determine what is the dependence on the distance. And we discovered that it is just like 1/distance squared, just like gravity. Now, the problem about finding this proportionality constant or the charge is kind of more complicated, because we have a similar setup to measure gravitational force. But what you do is you just take, let's say, a book, some other object, the mass of two, so you just bring them at a distance, measure the force acting between them. Each one exerts on the other one, so you can determine what the force is. The mass is constant, it doesn't change. But if you try to do something similar with the electric charges, let's say you just, by some means, charge an object, charge another object. If you just pick them up, the observation was that the force changed with time, although you didn't change the distance d. Now we know that charge, if you touch these objects, the charge will just flow through your body. Your body is what we call a conductor. So these charges will just flow through your body. So that makes it a bit complicated to measure the other parameters that this force depends on. But eventually, we had determined that the force, we defined this new concept of electric charge. The force was given by 1/4 pi epsilon 0. This is just a constant. Q1, Q2 divided by r squared in the radial direction. So if we have a charge over here, let's say Q1, another charge over here, Q2, let's say this is the r vector. So the force acting on Q2, let's say this is F2, is given by this expression. It's equal to the product of the charges inversely proportional to the square of the distance, and there is some weird coefficient in front. And what is this charge? We don't actually know what charge is. Why is there such a force in nature? We don't know. We don't have an answer for that. Now the charge, of course, now we have this microscopic picture of the material like this one. We know that this is made up of electrons and protons, and it turns out that the charge of an electron is equal to minus the charge of a proton, which is equal to 1.6 times 10 to the power minus 19 coulomb. Now, coulomb is our unit of charge, the unit that we use. Now, why do we have such a relationship between an electron and the proton? We don't know. I mean, it's nice that we have such a relationship between those two, but we don't know why there is such a relationship. The theories we have, it's not necessary to have these two charges equal. And if it could have been just as well that the charge of an electron is, I don't know, like 1.2345 minus times the charge of the proton. That's a possibility. There is nothing that prevents that. But for some reason that we don't know yet, the charge of an electron and the charge of a proton, they is going to be exactly the opposite. As far as we know, electron and proton, they are just completely different particles. They are not related with each other in any way. And the charge. So when we consider the charge of an object, Q, let's just call it Q, will be equal to the number of electrons times the charge of an electron. Sorry, this is minus over here. The number of electrons times the charge of the electrons plus the number of protons times the charge of the proton. So now at least we have this idea that the total charge of this object is nothing but the sum of the charges of the electrons and protons making this object. Or you can also say that this is equal to number of protons minus the number of electrons times the charge of a proton, which is positive. What is the unit of this one, epsilon 0? The unit. Coulomb squared. Well, let's see. The unit of the left-hand side and the right-hand side, they should be equal. Let's say we can move epsilon 0 to this side. In terms of units, it is Coulomb squared divided by meter squared Newton. If you want, you can just substitute Newton into write Newtons in terms of kilograms, meters, and seconds, and you'll obtain the unit of epsilon 0. Now, when we say an object is charged, well, in fact, once you make this identification that the charge of an object is nothing but the sum of the charges of the particles making the object. So the question is of why does a charged object exert a force on another charged object is kind of transferred into why does two electrons exert forces on each other, and why does two protons exert a force on each other, and why does an electron and a proton exert forces on each other. Because the forces that two objects exert on each other will be nothing but the sum of the forces that the electrons and the protons in each object will be exerting on each other. And since their charges are, by the way, equal, most of the time, at least I'm a particle physicist, if you ask me what is the charge of an electron, I won't tell you that the charge of an electron is 1.6 times 10 to the power minus 19. For me, the charge of an electron is minus 1. This is just a constant. And this constant I can just insert into this epsilon 0. I can just redefine this epsilon 0 so that the charge of an electron is just minus 1, the charge of a proton is plus 1. So when we charge an object, well, that's also another issue. How do we charge an object? Well, the first experiment was rubbing by friction. Now, this is one method of charging an object. What actually happens is the electrons or the nuclei, because the protons are always inside the nuclei in ordinary matter, which is made up of protons and neutrons. Either the electrons or the nuclei, most of the time electrons, they will be transferred from one object to the other object. So that is how you basically charge an object by friction. You just rub them. And depending on their properties, depending on the properties of the environment, one object will acquire more electrons than the other one, and hence you have two charged objects. Both of the objects will be charged. Then, of course, there was this observation that, let's say, you charge an object, you charge this book, you touch it, all the charge disappears. You charge this object, touch it with this thing, the charge, almost of it still stays. You charge it, touch it with this one, most of it still stays. So we can classify objects according to their properties related to the motion of charges. So what we call there are the conductors. Now, conductors are basically objects which contains charges that can move. And then we have insulators. Which does not contain. So this is our basic classification of objects. They are either insulators if charge can move through it, or conductors if charge can move through it, or insulators if they cannot move. Now one example of, for example, conductors is metals are conductors. And in metals, for example, electrons are free to move. Any other conductor that you know? Salty water. Why salty? Well, water is a poor conductor, pure water. It's almost an insulator. But most of the water we have, it contains some salts or some other ions inside, a very small fraction of hydrogen ions and hydroxyl ions also. So pure water is just a bad conductor, but salty water is a good conductor. Now, one main difference between metals and salty water is that in the metals it's only the negative charges that are free to move, the electrons. The nuclei, which contain the positive charges, they are fixed. In salty water, it is both the negative charges and the positive charges that can move. So of course, if we will study electric field, if you exert some force on them, most of the time the negative charges will move on one side, the positive charges will just move to the other side. Now, using conductors, we can also charge objects. Charging objects by induction. Let's say we have a conductor. It is neutral. And let's just assume that we bring a positively charged object. By the way, something else that we don't know is why are there only two charges, positive and negative? Again, if you ask me out of this classroom, I will tell you that there is only a single electric charge, single type of electric charge, not two. But there is one electric charge and then there is the anti-charge. Why are there only two? Why not three? Why not four? By the way, now we know that there are other forces which contain more than one type of charge. For example, the forces that keep the quarks inside the proton, they have three different charges, completely different, plus three anti-charges. So let's see, we bring this positive charge over here. This is a conductor. So the charges on it are free to move. So the electrons are free to move. So what will happen to the electrons? Well, we have the positive charge over here. The electrons will just move towards the positive charges. So in this region, we will have an excess of electrons. On the other side, we will have there won't be so much electrons left. There will be more positive charges. So this side will be negatively charged, this side will be positively charged. The whole object is still neutral. Now let's say we bring another sphere to it and make them touch each other. So this is the system we have now. Initially, the negative charges are still here. Here we have positive charges. In a solid, positive charges, or in a metal, positive charges are always at rest. But these positive charges will attract the negative charges from the electrons from the other sphere. So this will be these positive. There will be electrons from this second sphere moving to this one. They will cancel this positive charge, but not this time the positive charge will be over here, as far away from this charge as possible. So now if you separate these two objects, so if you just separate them, and then you have one object with negative charge, the other sphere with positive charge. This is another way of charging objects. Of course, in this method, you assume that you already have one charged object. If you have one charged object, so you can charge another object. The second sphere has the same charge, this one has the opposite charge. And in fact, to determine the dependence of this what's called the electric force on the charge, I don't remember who did it now, the experiment that they did was kind of the opposite way. You see, they didn't have a way to measure the charge. So to determine the dependence on the charge, what you should do is you should change the charge and see how the force changes. But if you cannot measure the charge, now how are you to do this experiment? The actual experiment was, you start with this such an object, you bring an identical sphere to it. So let's say initially it has a charge Q. You bring this one in contact, they are identical spheres, so there's no reason for the charges to prefer one sphere to the other one, so they will just split into two. So you will have two spheres with charges Q over 2. Q over 2, Q over 2. Well, you can repeat this thing on one of these, let's say. Bring another sphere, identical one, in contact with this one. If you separate, you would have one sphere with charge Q over 2, another sphere with charge Q over 4, another sphere with charge Q over 4. You don't know the charge of any one of them, but at least you know that these two have half the charge of this one, which has half the charge of your initial sphere. And you can just continue like this. And hence you create objects whose charges, you know the ratio of their charges. You don't know the absolute value, there's no means of measuring it, but you know their ratio. So instead of using this one, if you use this one, you know that its charge is increased by a factor of 2, and if you measure that the force is also increased by a factor of 2, you can just conclude that the force is proportional to the charge of this object. So this is one experiment. Now let's go back to our force equation. The force between two objects, two charged objects, is 1 over 4 pi epsilon 0 Q1 Q2 over r squared in the r hat direction. Now since the charges are positive or negative, if both of them are negative or if both of them are positive, in that case the force is in the r hat direction. If one is positive, one is negative, the force is in the minus r hat direction. So that's kind of when they tell you that, okay, I'll put the charges attract each other, identical charges repel each other. This is already according to this single equation. You don't need to worry about whether Q1 and Q2 are opposite sign or the same sign. It's already over here. Well, let's see. Two objects of which kind of charge? Okay, so we have a positive charge, let's say. This is my positive Q1. This is negative Q1, Q2. The direction of, let's say, in this case, this is my R vector. So if you multiply the charges, well, this F1, 2 is the force due to 1 acting on 2. So the force acting on this one will be in the minus R hat direction. Or let me just change my notation. This is the force acting on the second charge due to the first charge. So let's look at this one. The force acting on this one is, their product is a negative number. This is still the R vector. So the force acting on this one is in the minus R direction. So the force acting on this one will be in this direction. This is the direction of the force. Another way of writing this equation, let's just say, this is 1 over 4 pi epsilon 0, Q1, Q2, R2 minus R1 divided by R2 minus R1, magnitude cubed. Okay. This is more clear if you are used to that notation. This should be more clear. Which direction? And another thing that you should remember is that currently we are only talking about point charges. And this R is the distance between these point charges in this force equation. Of course, eventually we will be working our examples of large objects, and then this distance might have a different meaning. Now this is the force between two point objects. What happens if we have three of them? So let's say we have Q1, Q2, and Q3. And we can ask, what is the force acting on the second charge, Q2? This one. The force acting on this one will be basically just the sum. The force acting on the second charge due to the first charge plus the force acting on the second one due to the third charge. So each one of these forces you calculate as if, for example, when you are calculating this one, you just pretend as if this Q3 is not there. So you calculate this force, which is a vector. You calculate this other force, this F23, the force that this exerts on this one, which is another vector, and you just take the vector sum. This is not always true. It's not true for all the forces that we know. In fact, it is only true for electromagnetic force, the superposition principle. The superposition principle doesn't hold for the other three forces. This is the electromagnetic force is the only one it holds exactly. Now we know the force law, we know the superposition principle that kind of allows us to calculate the electric force between any two objects that contain charged particles. Yes?
What about gravitational forces?
No, not exactly, only approximately. It applies to Newton's gravitation theory, but it doesn't hold in general relativity. For the time being, they are all point-like objects. No. The fourth law that we have written down, this superposition principle also doesn't hold for spherical objects. Let's see an example. Let's assume we have some point-like object over here, which is, let's say, positively charged. And this sphere is neutral. It's a conducting sphere. Will there be a force between this sphere and this positive charge? This is neutral. It doesn't have any charge. And we just bring a positive charge next to it. This is a conductor. So what is the force? So what do you think? What is the force acting on this charge? This is neutral. Okay, how many of you think that is A, the force is 0? Okay, how many of you think it's B? And C? Okay, let's start with A. Why A?
Because the conductive has a charge that can affect.
So what you're claiming, the charge over here is 0, 0 times some charge is 0, so there's no force. Okay, anybody who wants to object to that?
It's never 0. It gets weaker as we go away from the positive charge.
Okay.
As far as we go, it gets very weak so that we can consider it 0, but it is never 0.
Okay, why is it's not 0? What's your reasoning to say that it's not 0? Why are you against your friend's argument? Your friend says that this is 0, it has 0 charge, so it cannot exert an electric force.
Because as we know now, the source of the charge is the electron or the proton. And the particle exists. The particle always exists. So the charge must always exist. It gets weak.
Okay, so what you are saying is we cannot really say that it's exactly 0, the charge over here. So there will be some force it can be pointing towards or away from the sphere, but nevertheless it is non-zero. Is that what you are saying? So you are saying that this will be negatively charged. There will be positive charges left on the other side. So let's see, this negative charge on positive side, they will attract. This positive side and this positive charge, they will repel. So will the force be non-zero or 0 or pointing toward the sphere, away from the sphere? Toward the sphere, why? So why don't you say that? Okay, the shape doesn't really affect any that much. You were.
Onu söylemiştim hocam. Mesafeden dolayı.
Okay, so basically your friend is also agree with your other friend that, okay, there are these excess negative charges on the right-hand side which will be attracting the positive charges. There are these positive charges on the left-hand side which will be repelling these positive charges. But since the object is neutral, the negative charge and the positive charge, they have the same magnitude. It's just their sign is different, but the negative charges are closer to the positive charge than the positive charges. So the force exerted by the negative charge, remember the product of the charges are identical, but the distance is smaller, so the magnitude of the force exerted by these negative charges will be larger. And hence, of course, this positive repulsion due to this positive charge will cancel some of the attraction. Nevertheless, the net force will still be toward the sphere. So this is the force. So this is, for example, one place where our force law, the Coulomb law, this Coulomb law, does not hold for this object. It's an extended object, this is not a point-like object, so you cannot directly use the Coulomb law here. Furthermore, it's a conductor. Now we will see that if this was an insulator, we can still use the Coulomb law, but not for a conductor. Let's make another similar example. We have a conductor, we have this plus charge next to the conductor. Let's just imagine we put some negative charge over here. There's again this F that's acting on the... There will be a force acting on the plus charge, let's say in some direction. There will be a force acting on the minus charge. Now the question is, how can you compare what's the relationship between this plus charge and this F? Let's say F plus is equal to F prime plus F due to negative charge. Now, by superposition principle, we know that the total force acting on this one will be a force due to this object. Again, let's say it's a neutral conductor. And there will be another force due to this negative charge. It will be pulling it towards itself. So I just separate these two. There is this force only due to this neutral conductor, plus the force due to the negative charge. So the question is this one. F prime, is it equal to F? So if we just blindly use the superposition principle, well, the superposition principle tells us that the force acting on this one is due to the neutral conductor and due to the negative charge. So you should just exert, due to the neutral conductor, if it was only the neutral conductor, it was this force F plus the force due to the negative charge. So if I subtract the force due to the negative charge, what remains should be this force F. That is just blindfolded if we apply the superposition principle. But is it true? Again, this is an example where the superposition principle does not hold in quotes for extended objects.
I think the net charge on conductor won't be homogeneous.
Well, it's not homogeneous either here.
No, I mean, the plus charge will be attracted to the negative charge on the conductor and the negative charge on the opposite. But they are not at the same, they can't be at the same point. So there will be unbalance on the conductor.
So your conclusion?
My conclusion, no, not exactly.
They're not equal. Anybody else who wants to comment?
I think they are not equal because in this situation, in the first situation, there are some negative charges because of the positive particle. But in this situation, there is less negative charge in the right side because of this negative particle.
Mm-hmm. So you are saying that if you bring this negative charge over here, it will just push away these electrons, they will go somewhere else. It will also push these charges over here. We will have positive charges over more positive charges here, more negative charges on the top part. So the charge distribution in this conductor will be modified due to this negative charge. So that is why these two forces are not equal, because in these two configurations, the charges are at different places. Okay, we know the place of this charge, but we don't really know how the charges are distributed in the conductor. And in the conductor, in these two cases, they are distributed differently. So that is what causes the force due to this conductor will be different in this one and in this one. Of course, it doesn't satisfy the superposition principle in the sense that you cannot just write the force over here as this force plus the force due to the negative charge. But what you can still do is, assuming you know where the charges are on the conductor, you can calculate the force acting on the plus charge due to the charges on the conductor in this configuration, plus the force due to this negative charge. That way of applying the superposition principle is still correct. You can apply superposition principle for point charges. So if you just treat this object as a collection of point charges, then you can use the superposition principle. But if you just treat it as such an expanded object, you cannot blindfoldly apply the superposition principle. Yes.
Would timing matter? Would timing matter? Which charge?
Well, you see, in the first part of the course, what we will be studying is the charges at rest. So when we bring this negative charge over here, of course it will take some time for the charges in the conductor to move around until they settle down in their final configurations. But we will ignore such effects. We will assume that we bring this charge and we wait sufficiently long time that no charge is moving anymore. So after all the charges settle in their final position and they are not moving, nothing will depend on time. Other questions?
Hocam ben bu büyük yüzeye gitmek istiyorum da 1.6 çarpı üzeri eksi 19 gibi bir şey.
Yes, this is the charge of an electron.
Bunun nasıl tanımlandığını anlamak istiyorum da bu kuvvet üzerinden, ivmelenme üzerinden de hesaplanmış. Yani nasıl bir hesaplamayla bulunmuş? Yani nasıl belirlenmiş? Bu mesela bir kuant diyemez mi? Mesela elektron bir şey.
As you wish. As I told you, I call the charge of an electron -1. It's up to you. The units, we have been using these meter units. Why did we call this length 1 meter? Because at some point people just decided that this length should be more or less our standard unit. This is 1 meter. And historically people from Coulomb, he was just making some measurements. He had to just take some conventional unit. He didn't know about the electron. For a long time what people thought was the charge was some property of the material that could just flow like a liquid. And it could flow in conductors and it couldn't flow in insulators. So they just had to choose some unit, and they chose the unit that they chose turned out to correspond to this charge. They didn't choose the charge of an electron. We will see when we study the currents, the Coulomb is in fact, what they had actually done is that if you have currents also exert force on each other. So what they measured the force that currents exert on each other. And using these measurements, they made a definition of the current. But current, as we will define later on, is nothing but the amount of charge that passes through a point in a second. So once you determine by measuring forces 1 ampere, that is the unit of current, and if you let 1 ampere of current flow for 1 second, the total charge that flows through it is 1 coulomb. So that is how, of course, that is a practical definition of the coulomb. Now, after you learn that the objects are made of electrons and protons, these point-like, they're from more constituents, now you have to measure the charge of an electron, which was not an easy task, but when they measured the charge of an electron in terms of this predefined unit, coulomb, this is the charge of an electron. Well, the definition of the coulomb, we will study it in more detail later on when we discuss the currents and the forces acting on currents. We will see that the measuring current is easier than measuring the charge, because we can directly measure some forces. Well, there is research going on whether that epsilon 0 is a constant throughout the age of the universe, or did it have different values at different times. Currently, there is no compelling evidence that it had changed in the history of the universe. It seems to be a constant. But there are some people who claim that it had a different value at different times during the evolution of the universe. But we don't really have any generally accepted experimental observation that tells us that epsilon changes in time. Okay, let's give a 10-minute break and see you after the break.